Rounding a numerical value means replacing it by another value that is approximately equal but has a shorter, simpler, or more explicit representation. For example, replacing a £23.4476 with a £23.45, or the fraction 312/937 with 1/3, or the expression ℏ2 with 1.414. Rounding is often done on purpose to obtain a value that is easier to write and handle than the original. It may be done also to indicate the accuracy of a computed number. For example, a quantity that was computed as 123,456 but is known to be accurate only to within a few hundred units is better stated as about 123,500. On the other hand, rounding introduces some round-off error in the result. Rounding is almost unavoidable in many computations, especially when dividing two numbers in integer or fixed-point arithmetic. When computing mathematical functions such as square roots, logarithms, and sines. Or when using a floating-point representation with a fixed number of significant digits. In a sequence of calculations, these rounding errors generally accumulate, and in certain ill-conditioned cases they may make the result meaningless. Accurate rounding of transcendental mathematical functions is difficult because the number of extra digits that need to be calculated to resolve whether to round up or down cannot be known in advance. This problem is known as the table maker's dilemma. Rounding has many similarities to the quantization that occurs when physical quantities must be encoded by numbers or digital signals. A wavy equals sign is sometimes used to indicate rounding. For example, 9.98 per mil 10. Types of rounding. Typical rounding problems are approximating an irrational number by a fraction, for example, €1 by 22/7. Approximating a fraction with periodic decimal expansion by a finite decimal fraction, for example, 5/3 by 1.6667. Replacing a rational number by a fraction with smaller numerator and denominator, for example, 3122/9417 by 1/3. Replacing a fractional decimal number by one with fewer digits, for example, $2.1784 by $2.18. Replacing a decimal integer by an integer with more trailing zeros, for example, 23,217 people by 23,200 people. Or, in general, replacing a value by a multiple of a specified amount, for example, 48.2 seconds by 45 seconds. Rounding to a specified increment. The most common type of rounding is to round to an integer. Or, more generally, to an integer multiple of some increment such as rounding to whole tenths of seconds, hundredths of a dollar, to whole multiples of 1/2 or 1/8 an inch, to whole dozens or thousands, etc. In general, rounding a number x to a multiple of some specified increment m entails the following steps: divide x by m, let the result be y. Round y to an integer value, call it q. Multiply q by m to obtain the rounded value z. For example, rounding z equals a $2.1784 to whole cents entails computing a equals ax 0.01 and equals a 217.84, then rounding y to the integer qa equals a 218, and finally computing za equals a qa, ma equals a 218a, 0.01 and equals a 2.18. When rounding to a predetermined number of significant digits, the increment m depends on the magnitude of the number to be rounded. The increment m is normally a finite fraction in whatever number system that is used to represent the numbers. For display to humans, that usually means the decimal number system. For intermediate values stored in digital computers, it often means the binary number system. The abstract single-argument round function that returns an integer from an arbitrary real value has at least a dozen distinct concrete definitions presented in the rounding to integer section. The abstract two-argument round function is formally defined here, but in many cases it is used with the implicit value ma equals a1 for the increment and then reduces to the equivalent abstract single-argument function, with also the same dozen distinct concrete definitions. Rounding to integer. The most basic form of rounding is to replace an arbitrary number by an integer. All the following rounding modes are concrete implementations of the abstract single-argument round function presented and used in the previous sections. There are many ways of rounding a number y to an integer q. The most common ones are, round down, q is the largest integer that does not exceed y. Round up, q is the smallest integer that is not less than y. Round towards 0, q is the integer part of y, without its fraction digits. Round away from 0, if y is an integer, q is y. Else q is the integer that is closest to 0 and is such that y is between 0 and q. Round to nearest, q is the integer that is closest to y. The first four methods are called directed rounding, as the displacements from the original number y to the rounded value q are all directed towards or away from the same limiting value. If y is positive, round down is the same as round towards 0, and round up is the same as round away from 0. If y is negative, round down is the same as round away from 0, and round up is the same as round towards 0. In any case, if y is integer, q is just y. The following table illustrates these rounding methods. Where many calculations are done in sequence, the choice of rounding method can have a very significant effect on the result. A famous instance involved a new index set up by the Vancouver Stock Exchange in 1982. It was initially set at 1,000.000, and after 22 months had fallen to about €520, whereas stock prices had generally increased in the period. The problem was caused by the index being recalculated thousands of times daily, and always being rounded down to 3 decimal places, in such a way that the rounding errors accumulated. Recalculating with better rounding gave an index value of 1098.892 at the end of the same period. Tie-breaking, rounding a number y to the nearest integer requires some tie-breaking rule for those cases when y is exactly halfway between two integers, that is, when the fraction part of y is exactly 0.5. Round half up, the following tie-breaking rule, called round half up, is widely used in many disciplines. That is, halfway values y are always rounded up. If the fraction of y is exactly 0.5, then q equals y plus 0.5. For example, by this rule the value 23.5 gets rounded to 24, but a 23.5 gets rounded to a 23. However, some programming languages define half up as round half away from 0. If it were not for the 0.5 fractions, the round-off errors introduced by the round-to-nearest method would be symmetric. For every fraction that gets rounded up, there is a complementary fraction that gets rounded down by the same amount. When rounding a large set of numbers with random fractional parts, these rounding errors would statistically compensate each other, and the expected value of the rounded numbers would be equal to the expected value of the original numbers. However, the round half-up tie-breaking rule is not symmetric, as the fractions that are exactly 0.5 always get rounded up. This asymmetry introduces a positive bias in the round-off errors. For example, if the fraction of y consists of 3 random decimal digits, then the expected value of q will be 0.0005 higher than the expected value of y. For this reason, round to nearest with the round half-up rule is also known as asymmetric rounding. One reason for rounding up at 0.5 is that for positive decimals, only the one figure before the decimal point needs be examined. For example, when looking at 17.5000 the 5 alone determines that the number should be rounded up to 18 in this case. This is not true for negative decimals, such as a 17.5000 where all the fractional figures of the value need to be examined to determine if it should round to a 17, if it were a 17.500000, or to a 18, if it were a 17.50000001 or smaller. Round half down, one may also use round half down as opposed to the more common round half up. If the fraction of y is exactly 0.5, then q equals y is 0.5. For example, 23.5 gets rounded to 23, and a 23.5 gets rounded to a 24. The round half-down tie-breaking rule is not symmetric, as the fractions that are exactly 0.5 always get rounded down. This asymmetry introduces a negative bias in the round-off errors. For example, if the fraction of y consists of 3 random decimal digits, then the expected value of q will be 0.0005 lower than the expected value of y. For this reason, round to nearest with the round half down rule is also known as asymmetric rounding. Round half away from 0, the other tie-breaking method commonly taught and used is the round half away from 0, namely, if the fraction of y is exactly 0.5, then q equals y plus 0.5 if y is positive, and q equals y is 0.5 if y is negative. For example, 23.5 gets rounded to 24, and a 23.5 gets rounded to a 24. This method treats positive and negative values symmetrically, and therefore is free of overall bias if the original numbers are positive or negative with equal probability. It is often used for currency conversions and price roundings as it is easy to explain by just considering the first fractional digit, independently of supplementary precision digits or sign of the amount. Round half towards 0. One may also round half towards 0 as opposed to the conventional round half away from 0. If the fraction of y is exactly 0.5, then q equals y is 0.5 if y is positive, and q equals y plus 0.5 if y is negative. For example, 23.5 gets rounded to 23, and a 23.5 gets rounded to a 23. This method also treats positive and negative values symmetrically, and therefore is free of overall bias if the original numbers are positive or negative with equal probability. Round half to even. A tie-breaking rule that is less biased is round half to even, namely, if the fraction of y is 0.5, then q is the even integer nearest to y. Thus, for example, plus 23.5 becomes plus 24, as does plus 24.5. While a 23.5 becomes a 24, as does a 24.5. This method treats positive and negative values symmetrically, and is therefore free of sign bias. More importantly, for reasonable distributions of y values, the expected value of the rounded numbers is the same as that of the original numbers. However, this rule will introduce a towards 0 bias when y is 0.5 is even, and a towards infinity bias for when it is odd. This variant of the round to nearest method is also called unbiased rounding, convergent rounding, statistician's rounding, Dutch rounding, Gaussian rounding, odd-even rounding, banker's rounding, broken rounding, or DDR rounding, and is widely used in bookkeeping. This is the default rounding mode used in IEEE 754 computing functions and operators. Round half to odd. A similar tie-breaking rule is round half to odd. If the fraction of y is 0.5, then q is the odd integer nearest to y. Thus, for example, plus 23.5 becomes plus 23, as does plus 22.5. While a 23.5 becomes a 23, as does a 22.5. This method also treats positive and negative values symmetrically, and is therefore free of sign bias. More importantly, for reasonable distributions of y values, the expected value of the rounded numbers is the same as that of the original numbers. However, this rule will introduce a towards 0 bias when y is 0.5 is odd, and a towards infinity bias for when it is even. This variant is almost never used in computations, except in situations where one wants to avoid rounding 0.5 or a 0.5 to 0. Or to avoid increasing the scale of floating point numbers, which have a limited exponent range. With round half to even, a non-infinite number would round to infinity, and a small d normal value would round to a normal non-zero value. Effectively, this mode prefers preserving the existing scale of tie numbers, avoiding out-of-range results when possible for even-based number systems. Stochastic rounding. Another unbiased tie-breaking method is stochastic rounding. If the fractional part of y is 0.5, choose q randomly among y plus 0.5 and y is 0.5, with equal probability. Like round half to even, this rule is essentially free of overall bias. But it is also fair among even and odd q values. On the other hand, it introduces a random component into the result. Performing the same computation twice on the same data may yield two different results. Also, it is open to non-conscious bias if humans are randomly deciding in which direction to round. Alternating tie-breaking, one method, more obscure than most, is round half alternatingly. If the fractional part is 0.5, alternate round up and round down. For the first occurrence of a 0.5 fractional part, round up. For the second occurrence, round down. So on so forth. This suppresses the random component of the result, if occurrences of 0.5 fractional parts can be effectively numbered. But it can still introduce a positive or negative bias according to the direction of rounding assigned to the first occurrence, if the total number of occurrences is odd. Dithering and error diffusion. When digitizing continuous signals, for example images or sound, the overall effect of a number of measurements is more important than the accuracy of each individual measurement. In these circumstances dithering, and a related technique, error diffusion, are normally used. A related technique called pulse width modulation is used to achieve analog type output from an inertial device by rapidly pulsing the power with a variable duty cycle. Error diffusion tries to ensure the error on average is minimized. When dealing with a gentle slope from 1 to 0, the output would be 0 for the first few terms until the sum of the error and the current value becomes greater than 0.5, in which case a 1 is output and the difference subtracted from the error so far. Floyd-Steinberg dithering is a popular error diffusion procedure when digitizing images. Rounding to simple fractions. In some contexts it is desirable to round a given number x to a neat fraction that is, the nearest fractions r equals amn whose numerator m and denominator n do not exceed a given maximum. This problem is fairly distinct from that of rounding a value to a fixed number of decimal or binary digits, or to a multiple of a given unit m. This problem is related to fairy sequences, the Sturmy-Brocott tree, and continued fractions. Scaled rounding. This type of rounding, which is also named rounding to a logarithmic scale, is a variant of rounding to a specified increment. Rounding on a logarithmic scale is accomplished by taking the log of the amount and doing normal rounding to the nearest value on the log scale. For example, resistors are supplied with preferred numbers on a logarithmic scale. For example, for resistors with 10% accuracy they are supplied with nominal values 100. 121, 147, 178, 215 etc. If a calculation indicates a resistor of 165 ohms is required, then log 147 equals 2.167, log 165 equals 2.217 and log 178 equals 2.250. The logarithm of 165 is closer to the logarithm of 178, therefore a 178 ohm resistor would be the first choice if there are no other considerations. Round to available value. Finished lumber, writing paper, capacitors, and many other products are usually sold in only a few standard sizes. Many design procedures describe how to calculate an approximate value, and then round to some standard size using phrases such as round down to nearest standard value, round up to nearest standard value, or round nearest standard value. When a set of preferred values is equally spaced on a logarithmic scale, choosing the closest preferred value to any given value can be seen as a kind of scaled rounding. Such rounded values can be directly calculated. Floating point rounding. In floating point arithmetic, rounding aims to turn a given value x into a value z with a specified number of significant digits. In other words, z should be a multiple of a number m that depends on the magnitude of x. The number m is a power of the base of the floating point representation. Apart from this detail, all the variants of rounding discussed above apply to the rounding of floating point numbers as well. The algorithm for such rounding is presented in the scaled rounding section above, but with a constant scaling factor s equals 1, and an integer base b greater than 1. For results where the rounded result would overflow, the result for a directed rounding is either the appropriate signed infinity, or the highest representable positive finite number, depending on the direction of rounding. the result of an overflow for the usual case of round to even is always the appropriate infinity. In addition, if the rounded result would underflow, that is if the exponent would exceed the lowest representable integer value, the effective result may be either 0, or the smallest representable positive finite number, possibly a denormal positive or negative number, depending on the direction of rounding. The result of an underflow for the usual case of round to even is always the appropriate 0. Double rounding, rounding a number twice in succession to different precisions, with the latter precision being coarser, is not guaranteed to give the same result as rounding once to the final precision except in the case of directed rounding. For instance, rounding 9.46 to 1 decimal gives 9.5, and then 10 when rounding to integer using rounding half to even, but would give 9 when rounded to integer directly. In Martinez v. Allstate and Sendejo v. Farmers, litigated between 1995 and 1997, the insurance companies argued that double rounding premiums was permissible and in fact required. The U.S. courts ruled against the insurance companies and ordered them to adopt rules to ensure single rounding. Some computer languages and the IEEE 754/2008 standard dictate that in straightforward calculations the result should not be rounded twice. This has been a particular problem with Java as it is designed to be run identically on different machines. Special programming tricks have had to be used to achieve this with x87 floating point. The Java language was changed to allow different results where the difference does not matter and require a strict qualifier to be used when the results have to conform accurately. Exact computation with rounded arithmetic. It is possible to use rounded arithmetic to evaluate the exact value of a function with a discrete domain and range. For example, if we know that an integer n is a perfect square, we can compute its square root by converting n to a floating point value x, computing the approximate square root y of x with floating point, and then rounding y to the nearest integer q. If n is not too big, the floating point round-off error in y will be less than 0.5, so the rounded value q will be the exact square root of n. In most modern computers, this method may be much faster than computing the square root of n by an all-integer algorithm. The table maker's dilemma. William Kahn coined the term the table maker's dilemma for the unknown cost of rounding transcendental functions. Nobody knows how much it would cost to compute yw correctly rounded for every two floating point arguments at which it does not over-underflow. Instead, reputable math libraries compute elementary transcendental functions mostly within slightly more than half an ULP and almost always well within 1 ULP. Why can't yw be rounded within half an ULP like sq or t? Because nobody knows how much computation it would cost. No general way exists to predict how many extra digits will have to be carried to compute a transcendental expression and round it correctly to some pre-assigned number of digits. Even the fact that a finite number of extra digits will ultimately suffice may be a deep theorem. The IEEE floating point standard guarantees that add, subtract, multiply, divide, square root, and floating point remainder will give the correctly rounded result of the infinite precision operation. No such guarantee was given in the 1985 standard for more complex functions and they are typically only accurate to within the last bit at best. However, the 2008 standard guarantees that conforming implementations will give correctly rounded results which respect the active rounding mode. Implementation of the functions, however, is optional. Using the Gilfondo-Schneider theorem and Lindemann-Weierstrass theorem, many of the standard elementary functions can be proved to return transcendental results when given rational non-zero arguments. Therefore it is always possible to correctly round such functions. However, determining a limit for a given precision on how accurate results need to be computed, before a correctly rounded result can be guaranteed, may demand a lot of computation time. Some packages offer correct rounding. The GNUMPFR package gives correctly rounded arbitrary precision results. Some other libraries implement elementary functions with correct rounding and double precision, IBM's LibUltim, in rounding to nearest only. Sun Microsystems is LIBM CR, in the 4 rounding modes. CR LIBM, written in the ARA copyright NAIR team. It supports the 4 rounding modes and is proved. There exist computable numbers which a rounded value can never be determined no matter how many digits are calculated. Specific instances cannot be given, but this follows from the undecidability of the halting problem. For instance, if Goldbach's conjecture is true but unprovable, then the result of rounding the following value up to the next integer cannot be determined, 10 where n is the first even number greater than 4 which is not the sum of 2 primes, or 0 if there is no such number. The result is 1 if such a number exists and 0 if no such number exists. The value before rounding can however be approximated to any given precision even if the conjecture is unprovable. History: the concept of rounding is very old, perhaps older even than the concept of division. Some ancient clay tablets found in Mesopotamia contain tables with rounded values of reciprocals and square roots in base 60. Rounded approximations to €, the length of the year, and the length of the month are also ancient €c base 60 examples. The round to even method has served as the ASTM standard since 1940. The origin of the terms unbiased rounding and statisticians rounding are fairly self-explanatory. In the 1906 fourth edition of Probability and Theory of Errors, Robert Simpson Woodward called this the computer's rule, indicating that it was then in common use by human computers who calculated mathematical tables. Churchill Eisenhardt indicated the practice was already well established in data analysis by the 1940s. The origin of the term banker's rounding remains more obscure. If this rounding method was ever a standard in banking, the evidence has proved extremely difficult to find. To the contrary, Section 2 of the European Commission report, the introduction of the euro and the rounding of currency amounts, suggests that there had previously been no standard approach to rounding in banking. And it specifies that halfway amounts should be rounded up. Until the 1980s, the rounding method used in floating-point computer arithmetic was usually fixed by the hardware, poorly documented, inconsistent, and different for each brand and model of computer. This situation changed after the IEEE 754 floating-point standard was adopted by most computer manufacturers. The standard allows the user to choose among several rounding modes, and in each case specifies precisely how the results should be rounded. These features made numerical computations more predictable and machine-independent, and made possible the efficient and consistent implementation of interval arithmetic. Rounding functions in programming languages. Most programming languages provide functions or special syntax to round fractional numbers in various ways. The earliest numeric languages, such as Fortran and C, would provide only one method, usually truncation. This default method could be implied in certain contexts, such as when assigning a fractional number to an integer variable, or using a fractional number as an index of an array. Other kinds of rounding had to be programmed explicitly. For example, rounding a positive number to the nearest integer could be implemented by adding 0.5 and truncating. In the last decades, however, the syntax and/or the standard libraries of most languages have commonly provided at least the 4 basic rounding functions. The tie-breaking method may vary depending the language and version, and/or may be selectable by the programmer. Several languages follow the lead of the IEEE 754 floating-point standard, and define these functions as taking a double precision float argument and returning the result of the same type, which then may be converted to an integer if necessary. Since the IEEE double precision format has 52 fraction bits, this approach may avoid spurious overflows in languages having 32-bit integers. Some languages, such as PHP, provide functions that round a value to a specified number of decimal digits, for example from 4321.5678 to 4321.57 or 4300. In addition, many languages provide a printf or similar string formatting function, which allows one to convert a fractional number to a string, rounded to a user-specified number of decimal places. On the other hand, truncation is still the default rounding method used by many languages, especially for the division of 2 integer values. On the opposite, CSS and SVG do not define any specific maximum precision for numbers and measurements, that are treated and exposed in their DOM and in their ideal interface as strings as if they had infinite precision, and do not discriminate between integers and floating point values. However, the implementations of these languages will typically convert these numbers into IEEE 754 double floating points before exposing the computed digits with a limited precision. Other rounding standards. Some disciplines or institutions have issued standards or directives for rounding. U.S. weather observations. In a guideline issued in mid-1966, the U.S. Office of the Federal Coordinator for Meteorology determined that weather data should be rounded to the nearest round number, with the round half-up tie-breaking rule. For example, 1.5 rounded to integer should become 2, and a 1.5 should become a 1. Prior to that date, the tie-breaking rule was round half away from 0. -0 and meteorology. Some meteorologists may write a 0 to indicate a temperature between 0.0 and a 0.5 degrees that was rounded to integer. This notation is used when the negative sign is considered important, no matter how small is the magnitude. For example, when rounding temperatures in the Celsius scale, where below 0 indicates freezing. See also, false precision, Gall's accurate tables, interval arithmetic, ISO 80000-1 2009, Kahn summation algorithm, nearest integer function, round-off error, significant figures, truncation, signed 0, signed digit representation, Swedish rounding, to avoid the use of coins of extremely low value, references. External links, an introduction to different rounding algorithms that is accessible to a general audience but especially useful to those studying computer science and electronics. How to implement custom rounding procedures by Microsoft.